Welcome to the video for Chapter 18. Today we're going to derive two very important equations. The first is Poynting's theorem and the second is the wave equation. And both of these are going to come directly from Maxwell's equations that we saw last time. So we're going to learn a lot about Poynting's theorem. We're going to talk about the Poynting vector. We're also going to use the Maxwell's equations to derive a general homogeneous wave equation and a simplified one-dimensional wave equation, assuming there's a vacuum and that the electric and magnetic fields are polarized in only one direction. And then we're going to use Maxwell's equations to derive the speed of light. It's not too hard, again, to guess who I would pick as today's historical perspective. It's another old white guy. John Henry Poynting spent his life studying electromagnetic energy, elasticity, and astronomy. It was the 1800s. You could study a lot of different things back then. He coined the term greenhouse effect, which I find very interesting, and both the Poynting vector and Poynting's theorem are named in his honor. So let's talk a little bit about the Poynting theorem. So Poynting's theorem is going to give us an opportunity to be able to calculate the direction in which energy is flowing, or the direction of power flow, which it turns out is very hard if we didn't have Poynting's theorem. If we just had a function for E, even with a vector, and a function for H, even with a vector, it's not apparent from that which direction power is going to be flowing. And I understand, here's what I think is likely to happen today. I'm going to spend a lot of time talking about Poynting's theorem, and you are not going to see the point of it. No pun intended. You're going to find that this is tedious and uninteresting and unhelpful, and in about 3 chapters you're going to say, oh, now I understand why Poynting's theorem is so important. The Poynting vector is going to become one of our most important tools. So I guess just kind of stick with it for today. I'll try not to spend too much time on the derivations, try to spend more time on the examples, and then we'll get to the wave equation as well, which is probably the single most important result in all of electromagnetic field theory. So I want to start out with a copy of Faraday's law. I'm going to take H dotted with both sides of Faraday's law. And then I'm going to start with Ampere's law, and I'm going to take the dot product of E with both sides of Ampere's law. So I took originally Faraday's law, took H dotted with both sides, I took Ampere's law, took E dotted with both sides, and now I'm going to subtract equation 18.2 from equation 18.1. Again, you might say, I guess I can see what you're doing. I would have never been able to guess that I should have done this. How did somebody ever figure this out? And the answer is either super genius, which is probably the case, and or entire trash cans full of scratch paper that they spent probably 10 or 20 years thinking about this problem. So I'm taking each term of equation 18.1. You can see H dotted with the curl of E becomes H dotted with the curl of E. Negative H partial of B with respect to T becomes negative H partial of B with respect to T. And then I'm going to subtract the two terms of equation 18.2. So E dotted with the curl of H becomes negative E dotted with the curl of H. And this term, I won't read it out to you there, becomes this term right here. So we do in fact find that we can have one equation that kind of unites in a way a lot of the content of both Faraday's law and Ampere's law. Now we're going to apply a mathematical identity. Again, we could derive this, but it would take today, and I don't want to take an entire day to derive this. So we trust that mathematicians have done a thorough job of testing and verifying that this is correct. Notice how similar this portion of the equation is to this portion of the equation here. So in both cases, we have a dot product of a vector with a curl minus a dot product of a vector with the curl. I can identify that kind of B is equal to H and A is equal to E. So when I'm working with those variables, then I can use that. What I can do then is since these are equal to each other, I'm going to replace the left-hand side with the left-hand side. So it becomes the divergence of A cross B, since A is E and B is H, becomes the divergence of E cross H. And the right-hand side really remains unchanged in equation 18.5. I'm going to distribute E across the right side. So remember that here I have an E that's being dotted with 2 terms. I'm just distributing that E across the 2 terms. No other changes are occurring there. I'm trying to show very detailed steps here so that you can easily see the derivation of Poynting's theorem. Now let's concentrate on the first term on the right side. Sorry about that. So the first term on the right side is h dotted with the partial derivative of b with respect to t. Now we know that we can substitute b with mu times h, and that's all that I'm doing here in equation 18.7. So I end up with an expression that is, pull the mu out, that's a constant. It becomes h dh dt. And h dh dt actually kind of can appear right here. So I want this is kind of the most complicated step. It took me a long time to figure out this when I was doing this derivation. H dotted with dh dt sort of becomes this expression right here. But now let's come back over to here. So if I start with the derivative, partial derivative of h squared with respect to t, that's kind of the same thing as the partial derivative of h dotted with h with respect to t. But if I took the derivative, let's say the derivative of x squared with respect to t, well, I know that the power rule is going to give me a 2x, and then the chain rule is going to give me a dx dt. And so let me take this box out of here. This came from the power rule, and this came from the chain rule. So if you wanted to take the derivative of h squared with respect to t, you have a 2h times dh dt. And so although these are vectors, it's still the same idea. So notice that what I can do then is I can take equation 18.8. I'm going to divide it by 2. Sort of all three of those terms. I guess maybe it's the two right-hand terms are going to be divided by 2, and so I have h dotted with dh dt is equal to 1/2 times the partial derivative of h dot h with respect to t, and h dotted with h is actually going to be is no longer going to be a vector. It's going to be a scalar quantity. And if you dot product a vector with itself, so h dotted with h, you simply get the magnitude squared. So it's not an accident that this is not bolded. That's actually a scalar quantity. And so since that's a scalar quantity, it's going to make it easy for me to plug it back into the equation. A similar analysis on the second term. So let me come back up here. I had h dotted with dB dt, and now I'm going to have e dotted with dd dt. But remember that I could represent d as epsilon times e. And so I can do a similar analysis for e, and I end up with a similar term. So e dotted with de dt, and I know they're partial derivatives, is equal to 1/2 the partial with respect to time of e squared. So we can simplify that second term, the first term on the right hand side substantially, but I wanted to take some time to dive deeply into both of those terms because it's not apparent where this 1/2 comes from if you don't really pay attention. And I wanted to come up here and say that the 1/2 comes from this 2 right here, which is from the power law when you're taking the derivative of h squared. That I haven't actually seen that written in any textbook where the 1/2 comes from, and so I really wanted to emphasize where that's coming from. So we have the divergence of E cross H on the left. We now have a term that is strictly scalar on the right, and then we have a vector term on the right. So we still have a little bit of work to do here, but we're getting close. We're going to take a volume integral of both sides. If both sides are equal, then you can take the volume integral of two equal things, and the volume integrals will also be equal. We're going to apply Ohm's law to the right-hand side so that J is going to become sigma times E. And as we just saw, E dotted with E will give you the magnitude of E squared. We saw that for H and for E. And then let's see, we're also going to now apply the divergence theorem to the left-hand side. And the divergence theorem, you might remember, says that if you have the volume integral of the divergence of anything, where in this case that anything is E cross H, that's going to be equal to the surface integral of that thing. And in other words, if you've got a volume and there are some sources of vector inside of that volume, then you can determine how much source there is inside that volume by determining how much vector crosses the surface of that region. That's what the divergence theorem says. We introduced that last chapter. So we now have the final form of Poynting's theorem. It may not be helpful. You may not say I don't really understand what's going on here. But let's take some time and look at these three terms. each of these terms has a very physical significance. So we're going to start with the left-hand side. The factor E cross H is called the Poynting vector. And the fact that it's named after the same person who got the name on the theorem says that E cross H is going to be very important. We're going to represent E cross H as S. And this equation gets boxed because equation 18.15, the Poynting vector, may actually be even more important than the Poynting theorem. We won't be using the Poynting theorem every day, but we'll probably be using the Poynting vector almost every day. So the Poynting vector is very important. The Poynting vector, and this is a remarkable coincidence because the guy's name was Poynting, but the vector points in the direction of power flow. And so it's remarkable to me that that's the case. But S will always point in the direction where there is power flowing. So let's imagine that we have a circumstance where there's an E field here, and it's kind of hard to, I'll try to represent it as sort of flowing out of the page. So there's an H field that's flowing right here. And if you take E, I'm putting my fingers in the direction, so I'm putting my fingers in the direction of E. I have 4 fingers. And then when I curl my fingers so that now they are pointing toward me, then my thumb sticks out in this direction, which means that E cross H is in this direction. So S equals E crossed with H. And so I can see that if I have an E that's pointing upward and an H that's pointing out of the page, then that's going to result in power flowing toward the right. That's not at all apparent. It's not. There are some things in this book that are very intuitive, and you're like, yeah, I got it. That didn't really add a lot to my life. There are other things that it's like a mystery of the universe, and this is one of those. That if you take E cross H, it is the direction of power flow. So let me just take a minute and come back up here to Poynting's theorem and say we're taking a surface integral. So we're taking a surface integral of vectors that represent power flow. So we have a surface here, and there is maybe there's an S vector that's pointing out from the surface in all directions, for example. And if that S vector is pointing away and pointing out, remember that the surface integral of a closed surface is defined to be positive when pointing outward. So this means that the integral of over a surface area of E cross H with respect to S is equivalent to energy or power flowing out of the region. You know, the analog is if you think about, like, instead of energy, if you think about money. So this would be how much money do you spend every month? Or how much money do you spend in a certain amount of time? How many dollars per day do you spend? And so this is money that is leaving the system, where the system is your wallet, your purse, your checking account, and so forth. So this is money that is crossing the border, or energy that is crossing the border of the system, and it's leaving the system perhaps forever. Now let's look at the second term here. It turns out that the second term represents energy that is stored in the system. So this is like your bank account. So 1/2 times mu h squared, it represents the magnetic energy in the system, and 1/2 epsilon E squared represents the electric energy in the system. So you can remember that we've seen that, say for example in a capacitor, that there are electric fields in between the plates of the capacitor, and those electric fields are used to store energy. Similarly, if we have an inductor, which is really just a coil of wire, there's a magnetic field flowing up the middle, and that magnetic field can be used to store energy. Now we have an expression that represents how much energy is being stored. 1/2 mu h squared plus 1/2 epsilon E squared. It's likely in most cases that one of those two terms will be 0, because it's very unusual that you would have both a magnetic field and an electric field inside of a device, and both of them are being used to store energy. Most typically it's one or the other, or perhaps neither. In the example, say, of a resistor, there's no energy storage at all in a resistor. So in that case, we wouldn't have any expression, any quantity for this term. So let me just make a note here. This is power leaving the system. This is change in stored energy. And notice that there's a time derivative there, and so that's the time derivative of the change in stored energy, which is to say that it's a power. So it's really all three of these terms represent power. So the first is power leaving the system. The second is a delta E over delta T, which is like a power. And then the third term represents energy or power dissipated. So, if I had $1, I kind of have three choices. I can spend the dollar, and that would be this first term right here. I can save the dollar, which is this term right here. Or, if I'm extremely irresponsible, I could light the dollar on fire, or I could throw the dollar into a trash bin, and that would be dissipating the energy. And it's not irresponsible to dissipate energy. It is irresponsible to destroy money, and also a federal crime. But we will be dissipating energy all the time. We're dissipating energy anytime that we have a system that has resistance. And in particular, as you can see here, it is the conductance multiplied by the electric field squared, and you take the volume integral of that, and that gives the total power that's being dissipated by the system. So Poynting's theorem has some pretty significant sort of physical significance, physical meaning, if you look at those three terms. I go through quite a lot of space here to talk about, here we have an expression that represents the amount of energy that is stored in a system. Don't forget that we're actually taking the derivative of d with respect to t. I'm sorry, the derivative of w with respect to t. And then we also have to take the surface integral of, we have to take the volume integral of that. So that in order to get the final term in the Poynting's theorem, we have to do some more work on this. And then PL is the expression that we're using to represent the energy that is being dissipated, or the power that's being dissipated. And that's typically then turned into heat. If you think of a resistor, it's going to dissipate energy. It's going to convert electrical or magnetic potential energy. It's going to convert that into heat. I tried to draw a picture here that would help to represent what's going on with these three terms. There's the boundary of the system, which is the box. Energy can be stored as an electric field or a magnetic field, and that's where this W term comes in. Energy can be dissipated, and that's where we get this P sub L term right here. And then energy flowing is represented by the Poynting vector, S equals E cross H. And remember that the Poynting vector will always point in the direction of energy flow, but in the case of a closed surface, which is what we're going to be working with here, I just want to point out that I guess I wrote it somewhere. Okay, if the integral of S is positive, then net power is leaving the region or the system, and that's because pointing outward is positive for a surface integral. If the integral of S is negative, then power is flowing into the space, into the region. So just be aware of that we're talking about power flowing out being positive and power flowing in being negative. Okay, there's also a point form of Poynting's theorem, and that is going to represent, again, we have energy flowing in and out of the system, we have energy storage, and we have energy dissipation. So those three terms will always appear in any form of Poynting's theorem. Okay, it's time to tackle a pretty challenging example. This one, I probably spent about an hour working out my notes for this example. So let's tackle it here. We have a capacitor. We're accustomed to capacitors. We understand that there's an electric field in between them, in between the plates of the capacitor. I've indicated the dimensions of the capacitor here. It has a voltage that's being applied to it. But what we haven't in the past talked about, except when we were talking about displacement current, is that there's also going to be a magnetic field that is circulating around because of the changing the displacement current, the partial of d with respect to t. So let's go ahead and calculate a lot of things about this system. The problem statement just says analyze the power flowing, and so I didn't want to give away the punchline, but there's a pretty good punchline that's coming here. So first of all, let's start with Ampere's law. So Ampere's law says that the integral of h dot dl is equal to the surface, and that is a line integral, and that's equal to the surface integral of the partial of d with respect to t, displacement current, plus conduction current dotted with ds. Well, in this problem, there is no conduction current in between the plates of the capacitor because that's a vacuum. I guess you could say it's a dielectric, but in any case, it's an insulator, so there's no conduction current. So that's going to simplify our lives a little bit. I want to point out that the integral that we're doing here is around the perimeter, so it's the red dotted line. If you're watching this video, you can see that it's red. So we're going to go h times 2 pi a is the circumference of that circle, is equal to, now what is the partial of d with respect to t? Let me just make a note here that d is equal to epsilon times e. So this can be represented as epsilon times dE dt. So instead of dd dt, we're doing epsilon times dE dt multiplied by the surface area, and the surface area inside of here, so the surface area of that circle that we're working with is equal to pi a squared. So this a will cancel with this a, this pi will cancel with this pi, and h then is equal to epsilon a over 2 dE dt, which we can, let's see, I can write that E is equal to V divided by D. So I can write this then as epsilon A over 2 with a D in the denominator, dV dt. I don't really know what V is. It seems to have a symbol here that represents a sinusoid, but I'm just gonna leave it as a generic V for the moment. So H equals epsilon A over 2D dV dt. And that's from Ampere's law. Now, let's calculate the Poynting vector. So Poynting vector. That, of course, is E cross H. Let me write S equals. So S equals E cross H. And now we got to look at the picture here. Let me erase my notations on here. I'm going to put my fingers in the direction of the E field, and then I'm going to curve them, and this is really hard to represent. I can't do this without being there to show it to you in person, but if you do the cross product of E cross H, you end up with an S vector that is pointing inward. So S is pointing into the page. And I'm basically just going to be calculating the magnitude of S at this point, and I'm going to keep track of the direction as pointing inward, which I know it's going to yield a negative sign here, because remember that a positive integral is going to be pointing outward. So for right now, I'm going to have this is going to be negative, and then what is my quantity for E? Well, it's V divided by D. That came from right there. And then my quantity for H is epsilon A over 2D dV dt. And let's see if there's anything that cancels. Nope, there isn't. So let me get rid of those 4 fingers there. The magnitude of S is equal to minus epsilon A over 2D squared V dV dt. And now I'm going to take the surface integral. So the surface integral of, and again, I know that I've already accounted for the direction because I've added this negative sign right here. So I'm just going to be taking the integral of the magnitude of the Poynting vector, and that's going to be with respect to a surface integral. So that's over delta S. That's going to be equal to, and since the Poynting vector is going to be constant across that entire surface, the integral is just going to reduce down to a multiplication. So this is minus epsilon A over 2D squared times V dV dt. So that's the S. And now the area is going to be 2 pi AD. So that is the surface, and it's really hard to represent a three-dimensional object in a two-dimensional picture, but it is the sides of the cylinder here. So those sides of the cylinder, the circumference is 2 pi a multiplied by d. That's going to give you the volume. So this d will cancel with one of these d's, and this 2 will cancel with this 2, and there's an a that's going to get squared. So this is going to be minus epsilon times pi times pi a squared divided by d times v dv dt. And we could refer to this as P out. So P out is negative in this case because there's actually power flowing into the system. So now we can remind ourselves that we have an equation for C. The capacitance is epsilon times the area divided by the distance, divided by the thickness. Well, that's actually exactly this term right here, because pi a squared is the area. So we can now represent this as, let me get rid of those just so I'm not messing that up. So therefore, P out is negative CV dV dt. But remember what we know for a capacitor is that C dV dt is equal to the current. So this is minus I times V, which in fact we knew that already. We've seen this result before. We've never derived it in this level of detail, but we know that the power associated with any electrical component is the current multiplied by the voltage, and the negative sign there is indicating that power is actually flowing into the system. Okay, so we've finished the left-hand side of Poynting's theorem. Let's quickly tackle the right-hand side. I can make a note here that the power dissipation is equal to sigma times E squared, but sigma is equal to 0 because we're inside the capacitor. There's no conductivity inside the capacitor, so the dissipated power is equal to 0. So that's nice. We've got one term there that's going to go away. We also have, we can calculate this lowercase w. I put the little tail there on the end to represent that it's lowercase. So this is 1/2 times mu h squared plus epsilon e squared. And as I mentioned to you earlier, often one of those two terms is going to go away. In this case, we have electric fields that are storing energy, but no magnetic fields that are storing energy, so that term goes away. This becomes 1/2 epsilon e, but e is just v divided by d. Now I know that what I need to do is to calculate the time derivative of the volume integral of that quantity. So I'm going to have, I'll put the negative sign in there because that's in Poynting's theorem, the time derivative of the volume integral, so delta V of 1/2 epsilon, this should have been squared. So it's 1/2 E squared, and E is V over D. So it's 1/2 epsilon V over D squared, and that's dV. Now, we've got two different V's going on here, so I'm going to have to be careful about that. This V represents voltage, and this V represents volume, but very quickly here, that the volume V is going to go away, so we'll be okay. So this is negative partial with respect to T of 1/2 epsilon V squared over D squared times the volume of the entire capacitor, which is going to be pi a squared times d. So that d is going to cancel with one of these d's. Everything else there is a constant, so I'm going to bring out negative 1/2 epsilon pi a squared divided by d, and then it's the partial, it's a partial derivative, partial of v squared with respect to t. And so this becomes minus 1/2 epsilon pi a squared over d. The partial of v squared with respect to t gives me a 2v, and then the chain rule gives me partial of chain rule gives me 2v, and then just a dv dt. And I'm going to drop the partial there because there's really just a t dependence. So this 2 is going to cancel with this 2, and I'm left with negative epsilon pi a squared over d times v dv dt. And once again, I know that epsilon pi a squared over d is just equal to c. So this is minus c v dv dt. C dv dt is equal to the current. So this is negative I times v. And that is I guess you could say it's the partial derivative of the total energy divided by, or with respect to time. And so we have a quantity here, and we have a quantity here. And if we looked at Poynting's theorem, what we're going to find is that the P that is leaving the system is equal to negative derivative of W. That's the volume integral. So the capital W there is different than the lowercase w. Negative partial of W with derivative of W with respect to T plus the power that's being dissipated. There is no power that's being dissipated here. So what Poynting's theorem says is that negative IV should be equal to negative IV. Remembering that this negative sign right here is already accounted for in that negative sign right there. And so sure enough, we find not only can we calculate the power that's entering the system, not only can we calculate the power that's being stored in the energy of the system, but they in fact balance each other out. So this is one example that does seem to give us some support for Poynting's theorem being correct. Let's do a similar analysis, perhaps a bit easier, for an inductor. Now this inductor is being attached to a current source rather than a voltage source. I think that by seeing both of these, you'll sort of see the pattern, and it'll make it easier to see what's going on. We know that in inductors, primary energy storage, or its only energy storage, is in the magnetic flux density, or the magnetic field that goes through the core. But what we haven't seen up until this point is that the changing variability, or the change in H, is also going to induce an electric field that surrounds the inductor. Now that electric field comes and goes, and it doesn't have any energy associated with it, but the electric field will create a Poynting vector. So again, if we did E crossed H, and now we've got the drawbacks of not only am I not there, so I can't show you my right hand, but also this is a two-dimensional representation of a three-dimensional object. But what we find is that S points inward into the inductor. So we can do E cross H. Put your hand in the direction of E and curl it in the direction of H, and it will point inward. So I should mention that the E has arrows that are pointing upward like this. So you point your fingers upward, curl them in the direction of the H that's going to the right, and then your thumb will point inward. Okay, let's again start with Ampere's law. I'll go a bit more quickly here if I can. The integral of H dot dl is equal to the surface integral of the partial of d with respect to t plus j. So displacement current plus conduction current dotted with ds. We know that inside of this inductor there are no electric fields, and so therefore there is no displacement current flowing. And so therefore H times 2d, and remember that basically this is the same analysis that we've done in the past. H times 2d means that we have a path that's going through the middle, coming up, and then coming back again. H times 2d equals n times I, and H of the top, I should specify H of the top, is equal to ni divided by 2d, and H total is equal to H top plus H bottom, which is just ni over d. And then similarly we can write B, which is mu times H, is just mu ni divided by d. So that gives us either B or H, whichever one we need for the particular part of the problem that we're working on. I think I'm going to have enough space here that I can use. I'm going to be running a little bit short on space, so why don't I try to squeeze Faraday's law in right here to determine the electric field. So Faraday's law and Ampere's law, these are our two big guns. You know, we've also got Gauss's law for electric fields and Gauss's law for magnetic fields, but I mean, these are the two big ones, and so we'll be using those an awful lot. So I know that the integral of E dot dl is equal to negative surface integral of the partial of B with respect to T, and that's over a surface area. So E times the length of the E field, which is the circumference, 2 pi times A, is equal to negative partial of B with respect to T times the surface area, which is pi A squared. And so therefore, the E, let's see, I can cancel that A with that A and this pi with this pi. This is equal to negative 1/2 partial of B with respect to T, which is negative 1/2 partial with respect to T of mu Ni divided by D, because we just found mu Ni divided by D for B right there. So E is equal to negative, let's see, I can pull out, oh, I think I missed an A. Yeah, there was an A left over, so it's negative A over 2. Sorry about that, it's not just negative 1/2. So it's negative A over 2. So this becomes negative A over 2, and then we can pull the mu and the n and the d out. Mu n over d times the partial of I with respect to t. And I'm not sure if I can simplify that much more for the moment. Let's leave that as it is for now. That's the electric field. I can calculate the P out. Remember, that's the surface integral of the Poynting vector. So that's the integral over delta S of E cross H dot ds. That's equal to, and I know that it's pointing inward, so it's going to have a negative sign. And it's going to be the electric field, which I just found to be A over 2 times D, or mu n over D times di dt. And then the H field was Ni divided by D. And then the volume is 2 pi A, I'm sorry, the surface area is 2 pi A times D. So boy, this is getting to be quite an equation. The D's are going to cancel, the 2's can cancel, the pi, there's nothing to cancel the pi, and there's nothing to cancel the A. In fact, the A is going to get squared. So P out is equal to pi A squared mu n di dt, and there's n becomes n squared. There's also an I term, and the A is already squared, and I've already got the pi. Okay, so can I do anything else about this? I know, by the way, that L for this inductor is equal to mu n squared over D times pi A squared. So actually, yeah, here's the mu, here's the n squared, here's the, oh, I dropped a D. Sorry about that. So there's the D, there's the pi A squared. So this actually becomes L times I times di dt. But we know that for a negative sign, drop the negative sign, there's the negative sign. We know that for an inductor, L di dt is the voltage, so this again reduces to negative I times V. So that takes care of the left-hand side. As we saw in the previous example, P sub L is going to be equal to 0. There's no dissipation inside of this inductor. We also, we're going to find that W, the lowercase w, is 1/2 times epsilon E squared plus mu H squared, but there is no energy storage in the electric fields here. So I can do I can do minus dw dt, where that capital W represents the volume integral. So this is negative partial with respect to t of a volume integral of 1/2 mu H squared dV. So this is negative partial with respect to t of 1/2 times mu times my quantity of H. My H is Ni divided by D squared. And then the volume is going to be, the volume is pi A squared D. A lot of these are constants. Oh, and some of them can cancel. So there's a D that cancels. So I'm going to pull out negative 1/2 mu. N is inside the bracket, so it gets squared. So there's an N squared. There's a pi A squared. And then there's a D I squared dt. and then there is still a d in the denominator as well. So this is going to be equal to negative 1/2 mu n squared pi a squared divided by d, and then the derivative of I squared with respect to time is going to be 2I di dt. And the 2's are going to cancel, and so I'm left with negative mu n squared pi a squared over d times I di dt, and L is this term right here. So this term right here is L, so this becomes L times I di dt. Oh, I forgot the negative sign. And so this becomes negative I times V. So once again, we were able to calculate the energy that is leaving the system. It's negative, so it's actually entering the system, and that's the change that's occurring in the stored energy. So 100% of the energy that is entering this system is being stored in the form of magnetic fields. None of it is being dissipated, and none of it is being stored in the form of electric fields. Okay, everything else today should get quite a bit easier than that. Those two were substantially challenging and also very important derivations. So let's talk briefly about time harmonic electromagnetic fields. Time harmonic is simply a fancy way of saying that it has a time dependence that is entirely sinusoidal. So if you see something that says sine of omega t, then a fancy scientist would refer to that as time harmonic. So we're going to study a system in which electric fields and magnetic fields are both varying in time only sinusoidally. And so if we have a system that is entirely sinusoidal in time, we can apply phasors to solve that system, to help us analyze that system. And remember that the steps of working with phasors are replace the time dependence with an e to the j omega t, replace time derivatives with j omega. You would replace integrals with 1 over j omega, but we don't have any of those really that we're going to be working with. Solve the problem using complex numbers, and at the end, take the real part. Now, I basically just compressed about 3 weeks of circuit theory down to one sentence there, so if you aren't familiar with phasors, you need to go back and review them. If you are familiar with them, then they're going to work very well for us here. So given these guidelines, we can represent the time harmonic electric and magnetic fields as shown here. So assuming that originally they had an x, y, z, and t dependence, we're going to reduce this down so that the t dependence is only an e to the j omega t. Notice that there is no t dependence inside of here anymore. So e of x comma y comma z, we'll often represent this as e of r. And similarly, then we would have h of r, because the h dependence is also just x, y, and z. We can also then rewrite Maxwell's equations. And in this case, we're going to replace any derivatives with respect to time. We're going to replace those with j omega. And so we had a couple of derivatives, one in Faraday's law, one in Ampere's law, and the contents of Gauss's law for electric and magnetic fields are going to remain unchanged. So it's really this j omega right here and this j omega right here that are going to yield important changes to the system. So let's give some special attention to the phasor form of Ampere's law. So this equation right here, equation 18.21, notice that we can replace the j of r with sigma times e of r using Ohm's law. And if we did that, now the right-hand side has two terms with an e of r in them. So we can factor e of r out of both of them, and we end up with an expression that is very interesting. It has j omega epsilon plus sigma. Well, let's remember that this term right here is the conduction current, and this term right here originally came from the displacement current. So I'm going to explicitly label those in two additional equations here, where I've labeled the conduction current sigma times E, and the displacement current is j omega epsilon times E. Remember that in a very good conductor, the conduction current is much, much greater than the displacement current, while in a very good insulator, the displacement current is much, much greater than the conduction current. I guess if you had something that was halfway in between, like if J sub C equals J sub D, then that would be a material that is right at the boundary between being a good conductor and being a good insulator. We're also going to notice that displacement current increases as the frequency increases. Notice that up here, there's an omega dependence. So this omega dependence in the displacement current means that as the frequency of those sinusoidal waves increases, the displacement current is going to increase. The conduction current is going to remain the same. So if you think of this, if you have a plot of omega here, and I'm going to have J sub C is going to be constant, and maybe at very low frequencies, maybe there is no displacement current, but as I increase frequency, I'm increasing the displacement current until eventually they're going to cross. And when they cross, J sub D is going to be equal to J sub C. And when that happens, that's the boundary where this material is really no longer behaving like a conductor, and it begins to behave like an insulator. It's an interesting result here of studying the sinusoidal sort of time harmonic systems, is that we can see that eventually every conductor is going to begin to behave like an insulator. That will really put some constraints on us. It's going to mean that we're going to have some requirements of very high levels of conductivity to be working at high frequencies. So determine the frequency at which copper behaves more as an insulator than as a conductor. Well, what I want is the boundary here. So that boundary is going to be where sigma times E of R is equal to J omega epsilon times E of R. And I really just care about the magnitude, so I can drop the J there. So sigma times E of R equals omega times epsilon times E of R. Cancel out the E of R's. Sigma equals omega over omega times epsilon, but what I'm trying to solve for here is omega. Omega is sigma divided by epsilon, which in this case, we're told that for copper, the conductivity is 6 times 10 to the 7th. So it's 6 times 10 to the 7th divided by epsilon, which in this case is just epsilon 0, 8.854 times 10 to the negative 12th. All the units are consistent SI units, so I don't need to worry about them. This is 6.78 times 10 to the 18th, not 8th, 10 to the 18th radians per second. And so if I wanted to know what is the frequency is omega divided by 2 pi, which is 1.08 times 10 to the 18th hertz. So yeah, it's an issue, but it's not an issue until you get up to 10 to the 18th hertz. And I don't know about you, but I've never had anything that was at 10 to the 18th hertz. I mean, yes, it can become a problem. Terahertz is 10 to the 12th. If you just went to 1,000,000 terahertz, then copper would no longer serve as a good conductor. But for the purposes of this class, it will still be a good conductor. Very briefly, if you have a sinusoidal system, so if you have a time harmonic system, you'll have to handle the Poynting vector a little bit differently. It's an average Poynting vector now, because obviously as the electric fields and magnetic fields increase and decrease, the amount of energy that's flowing is going to change. So we need to take an average over a whole cycle. That average is where this 1/2 comes from, because if each one of these, if E was an RMS value and H was an RMS value, when you multiply them together, those square root of 2's in the denominator become a 1/2. The only thing that I would just want to point out here is that you have to take the complex conjugate of H. So if H is given as, say, 2 plus J3, then the complex conjugate of that says, nope, it's not plus, it's minus. So you have to invert the sign of the imaginary part. Or if you were told that it was 5 at an angle of 45 degrees, nope, it's not 45 degrees anymore, now it's negative 45 degrees. So just realize that you either have to invert the sign of the imaginary part or the sign of the angle, and those are completely equivalent to each other. So given these values of E of R and H of R, calculate the average Poynting vector. So SAV is equal to 1/2 times the real part of E of R crossed with H star of R, which is equal to 1/2 times the real part of 100, and we have, there's an e to the j omega t, which is implied, but we can't imply the 30 degrees. So this is e to the j 30 degrees, and that's in the a sub x direction. And then that's going to be multiplied, whoops, can't close that quite yet. And that's going to be cross product with 0.265 e to the negative j 30 degrees. That negative sign comes from the fact that we have to take the complex conjugate of h. And then that's times a sub y. So this becomes 1/2 times 100 times 0.265, and then the e to the j30 cancels with the e to the negative j30. And a sub x crossed with a sub y gives me an a sub z, and so this becomes 13.25 a sub z, and the units of the Poynting vector are watts per square meter. Remember that if you take the surface integral of the Poynting vector, you end up with watts, so it has to be watts per square meter. Okay, that's enough on the Poynting vector for today. We'll see it again soon. But for now, we're just going to quickly, and we don't have to spend too much time on this, but it definitely is worth our time to think about deriving the wave equation from Maxwell's equations, because it is this derivation that unites electric fields, magnetic fields, and optics, or light. So it was the very first time that we realized that scientists realized that light is simply a form of electric and magnetic waves. So we're going to make a couple of assumptions here. We're going to begin with a fresh set of Maxwell's equations. We're omitting the harmonic form that we just talked about. So we're going back to old school. We're going to OG Maxwell's equations. Use the constitutive equations to eliminate D, B, and J. So we don't want D, B, and J to appear in Maxwell's equations. We only want E and H. So anytime that you have D, you can replace it with E by using epsilon. B can be replaced by H using mu, and J can be represented by E as well using sigma. So we're gonna do that. We're also going to assume that there's no charge density. That simplifies the right side of Gauss's law. So you can see here, this is because rho sub V equals 0. Everything else here is the same as we've seen in the past, except of course, as I mentioned, we've reduced this down to just E and H. All of the other variables are going away. They've been replaced with the constitutive equations. Now I should mention that really these two equations aren't going to be useful to us. We're really going to focus on Faraday's law and Ampere's law, and that's sort of the same thing that we did in deriving the Poynting theorem. It's just that now we're doing it to derive the wave equation. So let's take the curl of both sides of Faraday's law. So we start with Faraday's law, and we take the curl of both sides of Faraday's law. And we end up with equation 18.33. And I've pulled the mu out in front. I've pulled the partial derivative with respect to t out in front. Both of those are fine. I'm going to now substitute Ampere's law. So notice that I had a curl of h here, but Ampere's law gives me a quantity that is the curl of h. So I have epsilon dE dt, partial of e with respect to t, plus sigma times e. Now I'm going to distribute the time derivative on the right-hand side, so this time derivative here is going to move in to both of these terms. The first term already had a time derivative, so it becomes a second time derivative, but the other term had no time derivative. I'm also going to distribute the negative mu into those terms as well. Considering the left-hand side of this equation, we've seen this a lot of times. The curl of a function can be rewritten as the gradient of the divergence minus the Laplacian. And if we choose the Coulomb gauge, then that first term goes away, and the curl of the curl is just the negative Laplacian. We've actually seen that at least twice, I think 3 times so far in this class. So this reduces down to the left-hand side is just negative Laplacian of E, and the right-hand side remains unchanged from equation 18.35. I'll move the other two terms over to the left-hand side, multiply through everything by -1, and I end up with equation 18.38. And that is the wave equation. And it's a particular wave equation. It is the general homogeneous three-dimensional vector wave equation. I just want to mention that essentially we're going to find that the solutions to this equation will have the form of a wave. It can be polarized in any direction, and it can decay due to this term right here. So this term right here can lead to decay. That if you have a sinusoidal wave that is exponentially decaying, that's what I'm talking about by decay. So that decay would come from that third term. We don't like decay, at least for now. We're going to come back and see it later. But I want to know that if the sun emits a photon, if it emits an electromagnetic wave, I want to know that it's going to travel off into space until the end of the universe. And that's what we see. I mean, I can look out into the night sky and see light that was created billions of years ago. Maybe not with my eye, but with a telescope, I can see light from billions of years ago. Those electromagnetic waves have not decayed at all in billions of years. So in free space, in the vacuum of space, there is no decay. There is, I mean, very rarely will you encounter a physical particle in free space, and so very little of that wave will have decayed. Now, it turns out that we can do a similar derivation. I'm going to try to fit both of these on the, nope, can't fit them both at the same time. But equation 18.38, get a good look at that one. And then the next equation, 18.39, are identical to each other, except we use H instead of E. So this was done by a similar derivation. Here we start with taking the curl of both sides of Ampere's law, and then we substitute Faraday's law, rather than vice versa. That yields the same equation for H. And this is very interesting. The Ampere's law and Faraday's law, which came about from completely different perspectives, when we combine them together, they yield two equations that show that the behavior of E and the behavior of H will be exactly identical to each other. It's an underestimated result. That deserves some special consideration. We're going to go a step further. Since we already assumed that there was no charge density, it also seems reasonable to assume that there will be no conductivity. If there are no charges, it's difficult to have conductivity. Let me come back up here and mention that this decay term then is going to go to 0. So if this sigma goes to 0, then that whole third term is going to go to 0, and then I'm left with this equation, 18.40. And then I can assume that the wave is going to be polarized in only one direction. Oh, I should mention that we were studying waves in a vacuum, so we picked up the two subscripts here on mu sub 0 and epsilon 0. And now I'm going to assume that my wave is polarized in only one direction. It could be x, could be y, could be z, but I'm going to assume that it's in the y direction for this one case. And I can represent this as the normal one-dimensional scalar wave equation, which is typically represented as 1 over c squared in front of the time derivative term, because if you put it into that form, then c is the speed of propagation. It's the velocity of the wave. This could be the velocity of a wave of water, the velocity of a wave on a spring, the velocity of my voice through the air, or in this case, because we're talking about electromagnetic waves in a vacuum, it is the velocity of the speed of light in a vacuum. And since if I compare the mu sub 0 epsilon 0 to the 1 over c squared, I can then derive that c is 1 over the square root of mu sub 0 epsilon 0. And I'm going to guess that most of you probably have that value off the top of your head, 3 times 10 to the 8th meters per second. So let's verify that this is correct. So c is equal to 1 over the square root of epsilon 0 times mu sub 0, or I guess I wrote it in my notes as mu sub 0 times epsilon 0, which is equal to 1 over the square root of 1.2566 times 10 to the negative 6th. That's multiplied by 8.854 times 10 to the negative 12th. And if you plug those numbers into your calculator, you get 2.998 times 10 to the 8th meters per second. And for our purposes, I think you'll probably accept that that's close enough to 3 times 10 to the 8th. So the speed of light was hiding in Maxwell's equations all along. We just needed to convert it into the wave equation to be able to pull that out. So today we've talked about two very important principles. Trust me, you've not seen the last of either of these. We will be talking about Poynting vectors for a long time, and in particular the next several days of class we'll be talking, the next several chapters of the book, we'll be talking about the wave equation and looking at specific examples of how to apply it. So we saw the Poynting vector that can be used to determine the magnitude and direction of power flow. Poynting's theorem considers both power flowing in and out, and positive is out and negative is in. We see that there's a change in stored energy, and there's energy being dissipated in the system. You can have energy flow in and out, you can have energy that's being stored, and you can have energy that's being burned up. Poynting's theorem can also be written in point form. And we saw that Maxwell's equations can be rewritten in phasor form, and if we do that, then that means that the time dependence has to be sinusoidal, it has to be time harmonic, and that allows us to write two separate equations for conduction current and displacement current, and to determine whether a particular material is a conductor or an insulator at a particular frequency. Calculate the average Poynting vector in phasor form requires the use of the complex conjugate of H. And then Maxwell's equations can be used to derive a wave equation, both for E and H, although it's only shown for E here. The same equation can be derived for H, and those equations allow us to calculate the speed of light.